We present tracing versus freehand, an analysis using a new dataset to understand similarities and differences between tracing and freehand drawing, as well as to evaluate computer-generated drawing approximations. The computer graphics community has long been interested in developing methods to approximate what people draw. Computer-generated drawing approximation, or CGDA in short, can be divided into non-photorealistic rendering that takes a 3D mesh model as input, and image processing that takes a 2D raster image as input. Some widely used methods are suggestive contours, regions of valleys, apparent ridges, canny edges, and holistically nested edges. These computer-generated drawing approximations are often used as a proxy for hand drawings. For example, many rely on CGDA for training machine learning models. However, the extent to which current CGDA results resemble real drawing remains unclear. In particular, most CGDA methods only approximate the end result, neglecting the drawing process, which includes stroke and temporal information. This shows the importance of collecting and analyzing actual drawings so we can better model the drawing process and inform new algorithms. We consider two common forms of drawing, tracing and freehand. Tracings are easier to obtain than freehand drawings and are registered to images by definition. Like freehand drawing, tracing can also provide temporal information and stroke demarcation. The art community has long discussed the distinction between tracing and freehand drawing. For example, tracing is believed to help artists understand structure and perspective, but it can also discourage detailed analysis of the work and become a crutch. However, there is a lack of quantitative analysis. Such analysis would be meaningful as it would enable new paradigms for data collection and algorithm evaluation. There has been enormous work on datasets and algorithms for various drawing applications. Large-scale datasets like TU Berlin, Sketchy, and QuickDraw are intended for sketch recognition and image retrieval. While valuable for machine learning applications, many of these sketches are symbolic and do not reflect the complexity of observational drawing. In addition, tracings have been collected to study image segmentation and contour extraction. Tracing datasets like BSDL500 and PhotoSketch illustrate people's perception of edges and contours, which is essential to creating a good drawing. More related to our motivation are the drawing datasets used to understand how artists and designers draw, including Princeton, Portrait, and OpenSketch. The Princeton dataset laid the foundation for evaluating computer-generated drawing approximation, though it did not include temporal data or stroke for shading and texture. Portrait and OpenSketch include such information for a more detailed analysis of portrait drawing and technical drafting. Because it is hard to collect high-quality data, these datasets are relatively small. It remains necessary to create a dataset of time-stamped representational drawings with a wider variety of prompts, artists, and stroke types in order to further understand how people trace and draw. Our main contributions are a dataset of about 1,500 tracings and registered freehand drawings with temporal, vector, and pressure information. A spatial temporal analysis of tracing and freehand drawing, where we show their similarities in stroke placement and drawing progression. And a comparison of CGDA with hand drawing, where we show how much they overlap and suggest areas for improvement. In our study design, we included 100 photorealistic images with wide variations in appearance and content as prompts. More than half of the prompts have normal maps supporting our further analysis. Drawing typically employs a wide range of strokes, including contours, shading, and texture, so we did not limit the types of strokes that participants could draw. To collect normalized data, we imposed a time limit of 2 minutes, as we observed it was generally sufficient to complete a drawing. We implemented Speed Tracer, a web-based drawing interface using Vue.js. Participants were instructed to trace over the image using a digital stylus. They can select stroke width, color, and opacity, undo or redo a stroke, and clear the canvas. The interface for freehand drawing provides the same functions, except that participants were instructed to draw on the blank canvas on the right. There was a total of 110 participants. 85 were professional illustrators, experienced students from art and architecture schools, students enrolled in a college drawing class, or amateur drawing enthusiasts. To enrich the dataset with easier to collect cross-source data used in machine learning research, we recruited 25 participants from Amazon Mechanical Turk for tracing only. The resulting dataset has 1,210 tracings from 96 participants and 288 freehand drawings from 19 participants. 5 artists contributed both tracing and freehand drawings. We did not collect freehand drawings for 30 prompts of complex scenes, as it would be difficult to register them. Each of the remaining 70 prompts of single objects has about 12 tracings and 4 freehand drawings. The last step before our analysis is to register freehand drawings. We implemented a course to find optimization of image correlation between freehand drawing and tracing density using ITK. We initialized the displacement field using affine and B-spline transformations or manually labeled fiducials. We then obtained the optimal dense displacement field using gradient descent. Our analysis consists of 2 major parts. We first compare tracing and freehand drawing by examining their similarity in content drawn, stroke usage, and progression over time. We then evaluate CGDA methods by finding the overlap between their output and hand-drawn data. We start our analysis by exploring whether people trace and draw similar content using rasterized drawings. We computed pairwise distances to understand what people draw in common. For each pixel in a drawing, we recorded its closest distance to any pixel in other drawings. In both tracing and freehand, over half of the distances are within 4 pixels. This corresponds to commonly drawn content such as contours. About 15% of the distances are 20 pixels or more, which represents strokes distinct from each other. We obtain drawing density by superimposing all tracings and all registered freehand drawings for each image prompt. We then obtain binary commonly drawn regions by thresholding the density maps. Tracing and freehand drawing have similar CDR. Between them, over 80% of the pairwise distances are within 4 pixels. We found that over half of the pixels are common content in either form of drawing. People also draw similar common content between tracing and freehand drawing. We observe that this mostly occurs as silhouettes and interior contours of objects. To understand when people draw these common pixels, we divided the temporal span into 25 bins and counted the number of CDR pixels as well as all pixels drawn within each temporal bin. We found that in both tracing and freehand, the number of all pixels drawn is mostly uncorrelated with time. However, people tended to draw more common pixels early, and this tendency is stronger in tracing. We are also interested in how people's spatial focus changes over time. For CDR pixels of each prompt, we recorded their XY coordinates and their distance to the barycenter of the drawing. In tracing, dist-C decreases over time in 90% prompts, suggesting an outside to inside behavior. In freehand drawing, Y increases over time in 84% prompts, suggesting a top to bottom behavior. To understand this at a finer scale, we divided the temporal span of each drawing into 10 equal bins and took snapshots of the drawing in progress. We computed the convex hull area of each snapshot relative to that of the final drawing. We found that people tended to cover larger areas earlier in tracing. To sum up, people preferred finishing the entire outline first in tracing, as opposed to decomposing the prompt into parts in freehand drawing. This difference is more obvious when the prompt contains facial features catching artists' attention. The raster representation showed what people draw in common, but it missed stroke information. We now look into whether people use similar strokes using recorded vector data. We observed more flexible behaviors in freehand drawing. People tended to draw more strokes and also pause more, possibly because they needed to consider proportions. Overall, people drew similar amounts of content, but overdrawing is more common in freehand drawing. Stroke length is more evenly distributed in freehand drawing. This agrees with our observation. When tracing, people tended to draw long strokes as silhouette, followed by much shorter shading strokes. To examine trends in the drawing process, we evaluated a list of heuristics for stroke ordering. For each drawing, we performed the Monte Carlo sampling of all possible orderings. We then computed a score for each heuristic as the percent of random orderings whose energy was above that of the ground truth ordering. We found that overall, these heuristics characterize stroke ordering better in freehand drawing. Proximity is most important in both. Collinearity comes second and is less important in tracing. Simplicity is not as effective. People don't necessarily start with straight or constant curvature strokes. To further understand whether people use similar strokes in the drawing process, we extracted a list of stroke features and examined how they changed over time. We observed that in both tracing and freehand, stroke length, duration, and opacity tended to decrease over time. Speed and stroke width tended to increase over time. An inconsistency was pressure. People tended to apply more pressure when they started tracing contours than drawing them on a blank canvas. To sum up, we found that in both tracing and freehand drawing, early strokes tended to be long and drawn slowly using opaque colors. Late strokes tended to be short and drawn quickly using translucent colors. Changes in stroke features over time indicate that people might employ multiple types of strokes over time. Therefore, it is important to understand if tracing and freehand drawing evolve similarly. We manually labeled over 14,000 strokes in all tracings and freehand drawings for 10 prompts. We used two main categories, geometric contours and tone details. Geometric contours are further divided into silhouettes, interior contours, ridges, and valleys. Tone details are further divided into hatching, stipple, and texture. Overall, we observed that drawings progressed similarly in tracing and freehand drawing. Silhouettes were dominant at the beginning, and hatching strokes became more prominent towards the end. Trends in how stroke features and labels changed over time suggest the possibility of stroke classification. We built random forest classifiers using these features. The classifiers distinguish geometric contours from tone details with an accuracy of about 80 to 90% on splits of prompts, drawings, and strokes. Here we show sample label tracings used for training the classifiers. Orange represents geometric contours, and blue represents tone details. We trained the first classifier using 80% tracings and tested on the remaining tracings. We can see the prediction is very similar to the ground truth. We also trained another classifier using all tracings as training data and tested it on freehand drawings. The classifier was still able to predict the correct label for most strokes. To sum up, we found that spatial temporal stroke features can effectively characterize drawing intention. Classifiers learned from tracings can be transferred to freehand drawings. We now revisit current CGDA methods and evaluate their output using our data to see how similar drawing content is to computer-generated output. We began with a pixel-wise comparison between rasterized drawings and CGDA results. We computed precision as a fraction of CGDA pixels near any drawn pixel and computed recall the other way around. We considered 5 widely used CGDA algorithms and found about 60% of drawn content is consistent with computer-generated output. As shown here, NPR methods captured contours but did not consider texture information. Some image processing results contained incomplete or extraneous edges. Compared with CGDA results, drawings were cleaner, more organized, and contained interesting strokes that depict tone and shading. We also observed that CGDA achieved different performance on different images. For both tracing and freehand drawing, CGDA achieved lower precision recall on images containing background. The same trend was observed for images with texture. This agrees with our intuition because NPR typically does not consider image background or texture, and image processing output often includes extraneous edges from background and texture. To sum up, image attributes affect CGDA performance. This shows our dataset's value for identifying extensions to NPR and image processing algorithms that better approximate drawing, such as fusing different algorithms. We now examine how CGDA corresponds to common strokes. For each stroke, we computed a common score using drawing density to measure how well it covers commonly drawn regions. We also computed a CGDA score similarly. In tracing, we can see that early strokes tend to have high common and CGDA scores. We observed the same trend in freehand drawing. We ran a correlation analysis between both scores and stroke order and between the two scores for all strokes in each drawing. In both tracing and freehand, common and CGDA scores tend to decrease over time, and there is a strong positive correlation between the two scores. To sum up, CGDA methods can capture content that people commonly draw, but not people's diverse artistic conventions. We also compared our data with output from an NPR hatching algorithm, as people often depicted tone details using hatching. We composited all drawings for each prompt and blurred it to get areas of dense stroke coverage. We then compared it with a blurred version of NPR hatching. We computed the fraction of pixels in the blurred NPR hatching whose response was near that in the blurred drawing composite and vice versa. We found that less than half of drawn shading is consistent with NPR hatching. The hatching algorithm does not understand the semantics of the prompt, resulting in hatching patterns different from what people draw. The diversity of shading techniques presented in our dataset can inform new NPR hatching algorithms. Lastly, we examined which local properties contribute most to stroke placement, as CGDA output is derived from them. We show the 6 most important local properties in the table. We found that each property has comparable importance when used to predict stroke placement in tracing and freehand drawing, indicating similarity between the two forms. The high importance of n.v and image luminance shows the value of strokes for shading in our dataset compared to those containing only contours. To conclude, our dataset and analysis review the similarities and differences between freehand drawing, tracing, and computer-generated drawing approximation. Tracing is similar to freehand drawing in terms of temporal tendencies and representation choices, and thus can serve as a viable proxy for drawing. An analysis of the drawing process suggests that people's intention evolves over time, which can be characterized by similar spatial temporal stroke features. Current NPR and image processing results only capture 60% of drawn pixels on average, highlighting the great value of collecting hand-drawn data. Our study may have a few limitations. First, drawing habits may differ between digitized strokes from stylus input versus pen on paper, as well as when no time limit is imposed. Our registration of freehand drawings to tracings may introduce registration errors, and this form of normalization might mask artistic styles. We did not consider undo operations that might reveal useful information about revision and refinement. Our findings in comparing drawing to CGDA are specific to the commonly used algorithms that we considered. We think our dataset and analysis can be useful for many future applications, such as translation between image and drawing density, data-driven NPR methods that better emulate the drawing process, as well as recognition of different types of strokes and their customized treatment in sketching interfaces. For example, it would be very interesting to explore shape inference from strokes of different styles. We have made our dataset and code available to the research community, and you can find them on GitHub. Thank you for listening.